On number 42, now remember number 41 was asking us about whether the survey we did was biased or unbiased. Consider that as we go into the next question. We said that surveying every 7th student who enters the school is a good sample because it's random and also includes everybody in the population. Everybody had a chance to be asked. Number 42, so consider that. It says you want to determine the number of students in your school who have visited a theater, not a movie theater, but in like a play. You survey 50 students in the drama club. 26 have visited the theater and 24 have not. So you conclude that 52% of the students in your school have visited a theater. Now, by the way, 26 people out of 50 does equal 52%. So the math was done correctly. But I want you to tell me if that math is valid. Like, are the numbers valid? Can you use that information? What do you think, Hannah?
No, because the drama club is a middle school.
That's right. Yeah, this is not valid. Not valid because the sample only included students from the drama club. If we're being honest, they're the ones that are probably more likely to go to a theater than anyone else. So if your population is students in your school, number of students in your school, and then you only survey one particular part of that population, that is biased. And biased surveys give us invalid results. Number 43. It's just like what you guys have been doing with your survey projects, except this is a lot more people. You ask 120 randomly chosen students to name their favorite ice cream flavor. There are 1,800 students in your school. Based on the results of the survey, predict the number of students in the school whose ice cream flavor is chocolate chip. So on your survey, you predicted 25 people, or sorry, you surveyed 25 people and then made the prediction for 88 students in our hallway. They're surveying 120 because they have a much larger number of students. They're doing their entire school 1,800. So, but we're going to use a proportion nonetheless. The first ratio is going to be our sample ratio. And our second ratio is going to be our population ratio. So let's look at our sample. Sierra, can you tell me how many students that we sampled said that their favorite ice cream flavor was chocolate chip? 39. And how many students did we sample? That's right. I shouldn't say we sampled the students. That sounds weird. We surveyed them, and that was our sample. So if 39 out of 120 students voted for chocolate chip, what's our next ratio going to say, Frank? That's right. How many out of the entire population? So this is exactly what you guys have been doing to get your predicted number for your survey, except ours was out of 88. We surveyed 25, ours is out of 88. So we cross multiply this. Ella, can you tell me what 39 times 1,800 is? 70,200. Sorry, thank you. Is that right? Okay, I don't have my calculator, so I'm going off you guys. You checking yourself. Nobody raised their hand, so I'm assuming we're good here. And then Thomas, will you divide that by 120 and tell us what we get for our predicted number of chocolate chip lovers in the school? We'll bring it up here. Might have to fix it. You have a syntax error. Let's see if we typed in 20 log. What? Yeah, that's probably not going to give you the right answer. Okay, you feel comfortable doing it now? I just hit the clear button. Bring it up here. It might be jammed. I wonder if we got a button jammed in or something. Let me see what we got here. 20 log. Interesting. 120. Oh, sorry, we should be doing 70,200 divided by 120. You're right. It's not working. Let's see if we can. How about somebody else? You sure if I keep this one here? Okay, I'm going to explore this because I have the same type of calculator, so I think I could fix it for you later. Can you grab one of mine until then? Okay. Maddie Ann says, what did you get? 585. Okay, and then so on your paper, let's go ahead and label that students. And then on big ideas, go ahead and enter that 585 into the box. Okay. And we'll be ready for number 44. Okay, Thomas, I think you're good. I just did a hard reset on it and it seems to be working just fine now. Okay. By the way, if that happens again, see that button right here above the. Oh, putting the calculator back. Okay. See the reset right there above the number 0. See that second function 0. And then what it says, you just go over to where it says Y for yes, hit enter, reset, memory cleared. You're good to go now. Okay, number 44 is one that we are skipping. Now I'm going to read it to you because you could do it. I just don't have time for it. 5 classmates want to know how many of the 2,520 students in their school prefer pop music. So each of them survey 60 students. Shannon had 20 out of 60 students say pop. Trey had 23 out of 60 students say pop. Robert had 18 out of 60. Callie had 20 out of 60. And Lenny had 19 out of 60. So essentially what they want us to do is the same thing we did last time. 20 out of 60 is how many out of 2,520, except they want us to do that 5 times. And that's a bit redundant considering we just did that in the last problem. So I'm just going to go ahead and give you guys the answers to this. Yes, Jude?
Oh, well, my question was, can we just put like 55 after 53?
You are just, you don't have to write anything down on your paper. You just have to write the answers in the boxes. This is when we're skipping on the paper. So you're just writing the answers in on your boxes on big ideas. Okay. Brady predicted 840 students. Sorry, I said Brady. Where is Brady? Shannon. Brady Shannon predicted 840. Trey predicted 966. Robert predicted 756. Callie predicted 840. And Laney 798. And essentially just doing the proportion 5 times in a row there. Yes.
Oh.
Okay. Now for part B down here at the bottom, they want us to make inferences. So they want us to say what the greatest number is, what the least number is. So the greatest number, I'll just zoom out so you can see everything again. The greatest number we have here is 966. That goes in that first box, the greatest number box. The smallest, the least number we had was 756. So we're thinking if these 5 surveys got anywhere between 756 and 966, it's got to be somewhere between there. Yes, really?
That says Lonnie.
What did it says Lonnie?
Yeah, you kept saying Laney.
Oh, sorry.
That is Laney.
It looks like Laney.
No.
Laney says it's Laney.
That says Lonnie.
Or Lonnie. I thought Lonnie would be with an O though.
Huh?
L-O-N-I.
No, because it's so easy to make the A say the same.
I'll defer to Laney's expertise. What would you say that name is, Laney? Laney, okay.
Just say no.
Now, it says the median of the data is 840. By the way, if you line those numbers up from least to greatest, 840 will be right in the middle. That's what the median is. The mode, there was one number in there that repeated twice, also 840. And so they say that 840 is the number we should use because it's between the largest and the smallest surveyed predictions that we got. And it was also the median and the mode. So of course, 840 makes a lot of sense for this data. Okay, did everybody get all those boxes filled in? Yeah. Okay. All right, number 45 is also one that we're going to skip. Number 45, the tables show the ages of volunteers who attended 2 different survey projects. You can see the highway cleanup. There's 20 people and their ages up there. And in the soup kitchen, there's 20 people and their ages. Compare the populations using measures of center and variation. Your measures of center are mean and median and mode. Your measures of variation are range is what we talked about. They're using interquartile range here, which is something you talk about with box and whisker plots. We don't really get into that a whole lot here. They did, and that's something we skipped over, which is why I'm skipping this problem. The last one I skipped just because it was redundant. This one I'm skipping because we didn't get into this stuff other than median and mean and mode and range. So it says the distribution of the highway cleanup project is skewed to the right. So if I were to plot these ages onto what's called a dot plot, like I kind of just drew one over here on the up here, you're going to see that there's more people that are in their upper 40s and 50s than there are in their lower 40s or lower 30s or upper 30s. So it's skewed to the right. So because it's been skewed to the right, it's been pulled up. We shouldn't use the mean, as you guys might have expected. Not saying there's an outlier. I'm just saying it's been skewed one direction. So they're saying use the median and the interquartile range to describe the population. And so the measure of center, the median here, is 45, and the measure of variation is 3. So again, skewed right, median, interquartile range, 45, and the measure of variation is 3. For the soup kitchen, it is also skewed right, meaning that if I were to plot those ages, there's more people in their 30s and upper 20s than there are in their upper teens and lower 20s. So use the median interquartile range again. The mean is 25, or the median, I should say. The median is 25, and the measure of variation is 4. Okay. I think it's odd, though. If you look at this data, you would expect more of the older people to be helping in the soup kitchen, you would think, and more of the younger people to be helping out in the highway cleanup, since that'd be the more labor-intensive job. I feel like it should be reversed. You'd have the people in their 50s that are serving the soup and not picking up the trash on the highway. And then for part B, it's exactly what we said. The ages of those who attended the highway cleanup project are generally greater than those that are doing the soup kitchen. Yes. Okay, did everyone get that one there? Again, we're not writing this on paper, we're just, okay. So we'll move on to number 46. Oh, sorry, not the ones with the answers, the ones without the answers. Number 46. The probability of an event is 0.19. Describe the likelihood. Jude?
Unlikely.
Unlikely, yeah, 19% unlikely. Equally likely would be, or to happen is not. Remember we said this as likely as not. That'd be 50%, certain 100%, impossible 0%, unlikely between 0 and 50%. Number 47. Use the table to find the experimental probability. Now, experimental probability is based off of data that we've seen or that data that we have. Okay. Whereas theoretical probability is based on what we just assume is going to happen, what we know should happen. So I've got data here. Find the experimental probability of spinning a number on this spinner that's less than 4. What are the numbers on the spinner here that are less than 4? Maddie Cheeseman? 3, 2, and 1. Maddie Cheeseman, if you add all the times that the spinner was spun and you got a number that was less than 4, how many times did that happen? 31 times. So 11 and 9 make 20, plus 11 more is 31. So 31 times that happened out of, because it's a fraction, probability is, experimental probability. How many times did we see it happen versus how many times have we seen any number of spins happen? So we know that's 31. Add 6 to 31, that's 37. Add 6 to 37, you get 43. Add 7 to 43 and you get 50. So this would be 31 out of 50 spins, and that would be our fraction, except does that reduce?
No.
What number can go into 31 that can go into 50? Other than 1, just a 1. So this does not reduce, and so our fraction is 31 over 50. Okay. Number 48. Number 48 says use the table to find the relative frequency of spinning a 4. Now, relative frequency is the same as experimental probability. In fact, those words are interchangeable. Relative frequency means how many times did you see it happen over the total? Well, that's exactly what we just did. So spinning a 4. Now, by the way, these numbers are different than what we had in the last chart, so we're going to have to recount. Addison, how many times, Addison Stump, how many times was a 4 spun? 7 times. Okay, so 7 is going to be our numerator out of the total. So I have to count up again. 10 and 10 makes 20, 29. 29 plus 6 is 35. 35 plus 7 is 42. 42 plus 8 is 50 again. Now, this time, does 7 out of 50 reduce? Still no. Yeah, they don't have any common factors. So 7 out of 50 is our relative frequency, also known as the experimental probability. Number 49. Use the table to predict. Now, we're not doing probability right now. We're predicting. We're going to use a probability, but we're going to get an answer that's a prediction, a number of times. It's not going to be a fraction answer this time. Predict the number of times you would spin a 1 if you spin the spinner 100 times. Now, if this was based off of theoretical probability, and I'm assuming that the spinner has 6 equal sized sections, I would say that 1/6 of the time, you're going to spin that number 1. But I'm not using theoretical probability here. It says use the table. So I'm using experimental probability. And how many times, according to our table, our data, have we spun the number 1? 7 out of, is it 50 again? How many times have we spun? Let's count up. 7 and 8 makes 15. 7 and 8 makes 15. 15 and 15 makes 30. 11 and 9 makes 20. 30 and 20 make 50. It is 100 times, but that's what we're making our prediction out of. So what have we seen? 7 ones out of 50 spins. So if we've gotten a 1 7 out of 50 times, use a proportion because we're making a prediction. How many ones do you think we would get out of 100 times? Mental math says just times by 2, right? Yeah, I mean, you could cross multiply it, but you could just times by 2. What is 7 times 2? 14. Yeah. So X is 14. I expect 14 times that we get the number 1. Number 50. Number 50 says there are 5 yellow marbles and 8 orange marbles in a bag. You randomly choose one of the marbles. What's the probability that you'll choose yellow? How many marbles are we choosing? 1. How many fractions do we need? Just 1. This is simple probability. 1 fraction. Oops. And I'm choosing a yellow marble. So how many yellow marbles are there? 5. And how many total? 13. Does that reduce? All right, then that's my answer. Simple probability. Is that based off of theoretical or experimental probability? Yeah, it's theoretical. We don't have data on this. We haven't seen any marbles come out yet. We're just using common sense, what we know should happen. Number 51, a concession stand sells 50 drinks. 17 of those have been orange juice. What's the probability that the next drink sold will be orange juice? Is this theoretical or experimental? Yeah, this is based off of data. This is based off of what we've seen. So far, how many orange juices have been sold? Out of 50? That's our answer. That's the experimental probability that the next one will be orange juice. Now, the only way that you'll miss an experimental probability question like that is if you think next one means the 51st drink. It does, but you can't put the fraction out of 51. And you can't put the fraction out of 51 because you haven't sold that drink yet. We don't know what that drink will be. So we can only base it off of data that we've seen. We've only seen 50 drinks been sold. 17 out of 50 were orange juice. Number 52. You roll a 6-sided number cube and you flip a coin. How many events is that? 2. So how many fractions? Yep, we went from simple probability to compound probability. Just means we're going to multiply them together. And we're multiplying because the fundamental counting principle says that's what we do when we get our probabilities. If you're rolling a 6-sided number cube, it says a number greater than 1. How many numbers on this number cube are greater than 1? 5 of them. 2, 3, 4, 5, 6. So you have a 5 out of 6 chance of that happening. And what's the chances of flipping heads on a coin? 1/2. Anything cancel? Okay, 5 times 1, 6 times 2. Again, based off of theoretical probability. Theoretically, 5 out of 12 times, you would spin a number larger than 1 and then get a heads on 1. Number 53, find the total number of possible outcomes. This is, again, going to use the fundamental counting principle, but it's not a probability. Not sure why I just put FDC. Fundamental counting principle, FCP. We're not going to find a probability. We're not going to write our answer as a fraction. We're just finding the number of outcomes. So how many choices do we have for wallpaper? 3. And for carpet? And what do we do with those numbers? And that makes how many? 18 different options we could have, and 0 out of 18 are going in my house. I'm not putting red, purple, orange, blue, yellow, or green carpet anywhere in my house. And wallpaper is not going up either. Like maybe paint, I could paint something blue or green, purple,
Who would want a purple house? In the White House.
light purple.
For a daughter.
There's a lot of like the, yeah, like lavender colored
In
room.
the White House, there's 3 rooms, a red room, a green room, and a blue room.
Interesting.
I've seen it.
Have you been in them?
Yeah.
Really?
I've before the war, a whole White House. Crazy.
You shake hands with the president?
I wish.
All right. What was, where was your head at? Bonnie? Mhm. Our last one, number 54, says, a couple plans to have 4 children. The gender of each child is equally likely, as we know, we've kind of talked about that already. Design a simulation involving 55 trials that you can use to model the genders of the children. Write your answer as numbers. Okay, so they're saying that we could use coins. Why can coins be used to determine the gender of a baby? Hannah? Because why? Yeah, there's 2 genders and 2 options on a coin. Heads, tails, heads for boy, tails for girl, or vice versa. So they're saying that you could use a coin for each child. And how many children is this family wanting to have? So how many coins will we have to flip? 4. So they're saying you could use 4 coins. And if you want to run a simulation to kind of predict what you would get, they're going to want 55 trials. So how many times would you have to flip these 4 coins together? 55 times. And I bet you after 55 times, you're probably going to get a lot of 2 boy, 2 girl families. Because that's what we theoretically know should happen, because they're equally likely, 2 boys, 2 girls in a family of 4. But I know a lot of family of 4 that don't have 2 boys and 2 girls. So not guaranteed. Okay. So if you are finished, then here in a moment, I'm going to call you up to have you staple if you need to with your papers and turn them into the second period tray because the papers are worth a lot of points. Please double check that you have your name on everything. Okay. You're ready to submit if that's you. I'm not unsubmitting anybody's. So if you got one wrong, deal with it. If it says you got a 92.7%, that's because you paid attention 92.7% of the time because I gave you all the correct answers. Okay. Yes, question. Yes, Parker.
Can you go back to number 48?
48?
Yeah.
48. You got a what percent? You paid attention 91.7% of the time. You just missed 0.5, so you got a 99.5. What percentage did you say you got? 9.1. Okay, you have to watch the video. No, I'm not going back to any of them. They're all recorded. So go back to the day you missed. You can watch any and all of them. And this is due for the rest of you on Tuesday. But if you're ready to turn it in right now, go ahead and bring it up. Oh, no.
Are you leaving next year too?